Lots of time has passed since the Greek philosophers and their ideas about science. It's time for a new generation of scientists to come and try to do experiments that would actually come and try and figure out what is happening within the inside of an atom. So to begin with, we begin with a little bit of electrochemistry. There was an Italian scientist named Alessandro Volta, and he was interested in seeing if you could generate electricity. Electrochemistry is anything that can either use electricity to make chemistry happen or chemistry to make electricity happen. He wanted to create what we now know as a battery. And so this was really neat. This was a giant pile that you see here of dissimilar metals. So he would have copper and then zinc, and he would alternate, but he would do something here in the middle that was super important. He took kind of like cardboard-like substance and he smashed it between the two different types of metals, and what that did is it served as an electrolyte. And all batteries nowadays have an electrolyte in them, and that's what allows electrons to transfer from one material to the other, and as it's doing so, a current occurs, and that current is what powers your phone, your car, pretty much anything that runs on electricity. And so he created a really rudimentary battery, but it worked fantastic. You can still actually make these today if you just alternate like a quarter and then a penny, or probably a nickel and then a penny, nickel, penny, but in between them you need to sandwich some cardboard soaked in like a brine solution, a saltwater solution. So he played around in the lab and he found some really neat stuff. This pile is probably what he's known a whole lot for, but then also the unit volt is named after him. Next come guys such as William Nicholson, Anthony Carlisle, or Sir Humphrey Davy, and they all did some really interesting experiments. I particularly like Humphrey Davy's experiments where he realized he could control electrolysis, the use of electricity to generate chemistry. And so he started passing electricity through pretty much everything, pretty much like any child or person. Let's say you're sitting around a campfire and you realize stuff is going to glow different colors depending on what you throw in it. That's basically what he started doing. But obviously there's a little more control in his experimentation with tons of new elements that he created in the process. Then you have Michael Faraday coming around, who decides all this new stuff that we've got, it needs names such as ion, cathode, anode, electrodes, and he also improved on Volta's pile battery. So from here, we have this idea of electricity and the generation of current, but we still don't necessarily know about electrons, which is kind of funny. Electrochemistry was controlled prior to the understanding of real electrons. So we have J.J. Thomson. He was the one who first discovered the electron, and that was our first subatomic particle that was discovered. So what he did was he used Crookes cathode ray tubes, and so that's what you see here, which is basically you've got it evacuated of air. You can put different gases in there, but you have one is a cathode, one is a cathode, and one is an anode. And what's going to happen is you can apply a high voltage across those two dissimilar metals, just like in Voltaic's pile, but opposite, and see what happens. And what he noticed was he started seeing rays, and these rays are what you see over here with like fluorescent signs, or I don't know if you guys remember seeing these really old school monitors. They used to have a cathode ray in the back of them, and that's what illuminated the screen. But what he noticed is if you ran, so Crookes just developed this cathode ray, Thomson put negative and positive plates on it, and he saw that the ray went toward the positive side. So therefore he deduced correctly that those were negative particles because positives and negatives attract. So from this, he proposed his plum pudding model, is what it was called, which was the idea that we know atoms are neutral. So if they're neutral, but yet they've got this negative component, there must be something positive to balance it out. And so in this case, it's sort of like the sprinkles on the cookie, or in the cookie, or all around the cookie. Those were electrons, and then the dough itself is more of a mush that is a positive mushiness. But he envisioned them as really hard solids, but just within that is like a shotgun of electrons just randomly smattered throughout it. And so that was his first model. And it wasn't for many years that we were able to develop this atomic theory that we're going to come to later. So then Goldstein, he did kind of a similar experiment, but now he noticed what happened on the other side of the cathode, and that is that positive rays were being generated. So maybe it's not just a blob or a cookie dough, but maybe there's something more to the atom than just a positive blob, because now we've got electrons that can move and positive spheres that can move. Then Millikan, he used what's called an oil drop experiment to determine the charge of an electron. And what happens is as you drop it down here into a really fine mist, you control the force, the upward force on this electron here. And what happens is sort of like a teeter-totter. You know how if you hop on a teeter-totter, you go up and down, but then there's always that punk kid that's like, haha, I'm going to hold you in the air, and they have to exert a certain amount of force to hold the other kid up in the air. That's what was happening. And the amount of force that was required to be applied to hold it in the air is proportional to the mass of that electron. And so really clever experiment, but he was able to figure out pretty precisely the mass of an electron from this experimentation. So then from here, we then learned a little bit about radioactivity. A lot of good chemistry happens because of accidents. It's not just accidents, because if you're just a clumsy chemist and you just spill things everywhere and you just create accidents, that's one thing. But if you do something by accident, but then you have enough fortitude to notice what happened and to make observations, that's where accidents can turn into happy little Nobel Prizes. But in this case, you've got Berkeley, I think that's how you say his name. He was a professor that actually taught Marie Curie, and so he discovered radioactivity accidentally because he placed rocks on a photographic plate. And then he realized when he walked away that, hey, these photographic plates have been exposed, almost like they've been exposed to the sun. I wonder what's going on. And so he coined radioactivity, and he led to all of his discoveries were the precursors to even the X-rays that we do today. The Curies followed in their footsteps and did a whole bunch of experiments using radioactivity and went on to isolate many of these radioactive substances. These guys were all the precursors to a lot of the nuclear power that the scientists all around the world were facing and trying to create nuclear power and a nuclear bomb, if you will, at the end of World War II. So this bastard brigade that you see right here, Sam Keen is the author of the book The Disappearing Spoon that we're reading for this class. And this book I liked even more, sadly, because this is a physics book and the chemistry book is The Disappearing Spoon, but it's a really fun read. But it talks about all of what happened in the fight to try and be first in understanding atomic weaponry. So a lot of this radioactives was the precursor to a lot of that atomic bomb material. So, question for you. Is all radiation bad for you then? I mean, I just talked about bombs and exposing it. I mean, even the Curies, they died from a lot of the side effects of dealing with radiation. So, often when you see this radiation symbol, you're like, radiation is terrible. But I don't want you to think that, because a lot of radiation is good for you, such as light. Light is a form of radiation, visible or ultraviolet. Ultraviolet, even gamma rays now are being used and tested for their ability to clean and sanitize surfaces. So not all radiation is bad, but certainly some radiation can harm you, such as what we see here. We've got alpha, beta, and gamma rays. So alpha rays are actually positively charged particles, and they are the helium nucleus, basically. They're the least damaging. They can't penetrate your skin or your clothing. Beta is an electron, so it is negatively charged. It can penetrate your skin and your clothing. And then gamma rays, that's light, and that's actually the most damaging because it can penetrate your skin and can cause damage to your bones, your tissues, all of that. And so that's the type of radiation when a nuclear blast that is most damaging to people. All right, so with that, go read sections 3.4 and 3.5.